Hi folks, in this segment of our tutorial, we will be demonstrating how the atomic orbitals of carbon, nitrogen and oxygen undergo sp3 type of hybridization to form methane, ammonia and water molecules respectively. In this activity, we'll be using playdough to represent atomic orbitals. These here represent the 2s and the three 2p orbitals of the carbon atom as they exist in their ground state. As you can see, this s orbital here is spherical in shape and is having 2 electrons. And, like you said before, these are the three 2p dumbbell shape with 2 of them having 1 electron each, as represented by this orange ball here. And this one here is vacant. Here are 4 hydrogen atoms, each with a single electron, wanting to bond with these electrons here to form methane. However, as this model stands, we can see that there are only 2 single electrons here for bonding with hydrogen, but we are having 4 hydrogen atoms to bond. If bonding were to take place, only 2 of these hydrogen will have a chance to bond with these 2 single electrons. But empirical evidence shows that carbon is bonded to 4 hydrogen atoms in this methane molecule, and the arrangement of the bonds around the carbon atom is tetrahedral, with each having a bond angle of 109.5 degrees with respect to each other. And the geometry of the molecule is that of a tetrahedron. To account for the features of the methane molecule, as exemplified here, the theory of the hybridization of atomic orbitals is used. So this is the theory. The theory is that with an influx of energy, one of the electrons from this 2s orbital is promoted to this vacant 2p orbital here. Then simultaneously, all 4 of these orbitals get hybridized to form 4 sp3 hybrid orbitals. But before those 4 sp3 hybrid orbitals are formed, we could have envisioned that this red piece of Play-Doh, when mixed with these 3 pieces of white Play-Doh, we could have gotten a spherical piece of pink Play-Doh. And this piece of pink Play-Doh was divided into 4 pieces to form these 4 sp3 hybrid orbitals. So you can see that these are called sp3 hybrid orbitals because we are hybridizing this s orbital with these 3 p orbitals. So in the end, we're going to end up with 4 hybrid orbitals, and they're called sp3 hybrid orbitals, all because you're hybridizing one s orbital with 3 p orbitals. If you examine these closely, you can see they're all identical in shape, and they're having identical energy, and each one of them is having an electron. So now we're having adequate number of electrons to bond with these 4 hydrogen atoms there, each having a single electron. So that's the theory. Promote one of these electrons from this s orbital into the vacant p orbital. Hybridize all together, you end up with 4 identical sp3 hybrid orbitals. Our next job is to show how those orbitals there get arranged in such a way that when they bond with those 4 hydrogen atoms, you end up with this tetrahedral arrangement. So why do we have a tetrahedral arrangement? Recall that covalent bonds are negative in nature, and as a result of that, they will repel each as far away as possible to minimize the mutual force of repulsion between those bonds. And finally, they'll assume a tetrahedral arrangement. So our next job is to arrange these sp3 hybrid orbitals around the central carbon atom to show how they eventually bond with these 4 hydrogens. Assuming that this yellow styrofoam ball here is a carbon nucleus, here are the 4 sp3 hybrid orbitals, each with its single electron. Now we have 4 of these hydrogen atoms here, with their electrons can come and bond here, one here, another one here, another one here, and another one here. And finally, this is the model that we have here. This model represents the methane molecule. We are having 4 CH bonds arranged around the central carbon atom here. And each bond is separated from each other by an angle of 109.5 degrees. Geometry of this is said to be that of a tetrahedron. We now look at how the atomic orbitals of nitrogen undergo hybridization to form the ammonia molecule. Here again we are seeing that the 2s orbital is having 2 electrons. However, because nitrogen has 1 more electron than carbon, each of these p orbitals here will be having a single electrons. So people might want to say, look, you're having 3 single electrons here, and ammonia has 3 hydrogen inside its molecule. Why don't we bond these like these? 2, 4, 6, 8, and we would have had the octet. But remember that these guys here are mutually at right angles to each other. Had we done something like that, then these bonds here would have been at 90 degrees away from each other, and that would not have conformed to what the empirical evidence shows of 107 degrees. So the theory is, again, we hybridize the orbitals. We do not need to promote an electron, but instead, this 2s orbital with its 2 electrons get hybridized with these 3 p orbitals here, each having their single electron. And again, we produce 4 sp3 hybrid orbitals, but the only difference in this case is that you're going to have one of these with 2 electrons, and this will form a lone pair. Each of these now will be capable of bonding with a hydrogen atom. So you have 2, 4, 6, 8. So how do we put this around the central atom? Again, these 3 here will bond with a hydrogen each, and this one here will be represented as a lone pair. Note how it's still sp3 hybridized, and the bond angles here, because of this lone pair here, we get a bit little smaller, it become 107 degrees. Let that be a lone pair electron. The molecule will have a trigonal pyramidal shape. The bond angle is 107 degrees, and of course, the electron arrangement is always going to be tetrahedral arrangement. We'll now look at how the orbitals of the oxygen atom hybridize to form sp3 hybrid orbitals, as in a formation of water. Here is the 2s orbital with its 2 electrons. But now if you look at the p orbitals, one of them is having 2 electrons, and these 2 are having 1 electron each. Again, to account for the empirical evidence which shows that the bond angle between the 2 hydrogen atoms is 105.5 degrees, which indicates to us that it is a result of sp3 hybridization of the orbitals. People might want to say again that, look, you're having 2 p orbitals with a single electron each. Why don't we put a hydrogen there and hydrogen in one? Look what happens. You have 2, 4, 6, 8, and we would have the octet. But again, remember that these are at right angles to each other. So had you formed a bond here and a bond here, that would have only been 90 degrees. So the theory is that hybridization of the atomic orbitals take place again. What is it? We hybridize all of these here. What you're going to have is this. 2 of these here will have lone pairs, and only 2 of them will have single electrons in them. Placing these around the central oxygen atom, two of these will bond with hydrogen atoms, but these two here will represent lone pairs. And of course, the arrangement is tetrahedral for the atomic orbitals. So to make matters easy, we remove that one there. These are not bonds. I replace them by these lone pairs here. Assuming that that is a lone pair here, and this is the other lone pair here. This is what the molecule of water will look like. The oxygen atom undergoes sp3 hybridization. Two of these sp3 orbitals are bonded with hydrogen here. Okay? And the bond angle now, because of these two lone pairs, will be 105.5. And then you have two lone pairs there. The molecule is said to be a bent molecule or V-shape. Our next tutorial deals with sp3d and sp3d2 types of hybridization. Stay tuned and please don't forget to subscribe.